At the baseline of classical economics is decision-making under uncertainty. We model this with a coin flip lottery, a 50% chance to win 25 shekels or 75. The expected value is 50, but expected utility is subjective, dictated by your personal tolerance for risk. In 1944, von Neumann and Morgenstern formalized the classical view of this dynamic. They treated risk preference as an abstract mathematical parameter, defined by the concavity of utility curves. The problem with this classical theory is that utility curves do not exist in the physical world. They are invisible, internal cognitive states. If we want to design effective public pension policies or structure functional financial portfolios, we cannot rely on abstract theory. We have to derive these exact risk aversion parameters from real human choices. To observe this invisible trait, economists rely on highly controlled laboratory environments. They force subjects to make real wagers to reveal their actual risk tolerance. Classical expected utility theory operates on a strict assumption. A person's risk preference is a stable, mathematical constant that scales perfectly across different scenarios. Stress testing these models in the lab revealed a structural failure in that assumption. A person's risk preference is not a static constant. It bends predictably under the weight of high financial stakes and evaluation frequency. To measure risk, economists frequently use a functional form called constant relative risk aversion. Their primary goal is to isolate its core variable, the coefficient R. In 2002, Holt and Laurie designed an experiment to capture this using a multiple price list. Subjects face 10 paired lottery choices, comparing a safe option A to a risky option B. The probability of winning increments downward from 10 to 100. As a subject evaluates the list row by row, the rising probability of winning eventually forces them to abandon the safe option and switch to the risky one. This table shows how economists use that switch point. The row where a subject defects bounds their unobservable R parameter. For example, 6 safe choices maps cleanly to an R value between 0.41 and 0.68, classifying them as risk-averse. The multiple price list is precise, but it requires massive cognitive load. Processing these shifting probabilities is so complex that roughly 13% of test subjects produce inconsistent, logically impossible switch points. To solve the complexity issue, researchers Eckel and Grossman developed an alternative method, the simple gamble choice. It distills the test down to a single decision, forcing a direct trade-off between expected value and standard deviation. While these tools provide a quantitative estimate of R, using them to test real-world payoffs exposed a discrepancy between the model and actual behavior. The critical stress test was a simple question. Does a person's measured risk aversion remain constant if you multiply the financial stakes by 20, 50, or 90 times? This graph shows the proportion of safe choices. First, establish the theoretical baseline. The dashed line predicts a purely risk-neutral individual, switching exactly when the math dictates. The real-world low-stakes data, represented by the solid line with dots, sits firmly to the right of that baseline. Human behavior in the lab is decidedly risk-averse. But look at the anomaly that breaks the classical model. When the stakes are multiplied for real payouts, the choice curves shift progressively further to the right. As real monetary stakes scale up, people choose the safe option significantly more often. Risk aversion is strictly not invariant to scale. A second major flaw in classical theory stems from a famous proposition by economist Paul Samuelson. He offered a colleague a simple coin flip: win $200 on heads or lose $100 on tails. The colleague rejected the bet, stating the pain of a $100 loss outweighed the gain. But then he made a paradoxical counteroffer. He would accept the wager as long as Samuelson let him make 100 of those exact identical bets in a sequence. Samuelson proved this response violates expected utility maximization. Mathematically, if you reject a single bet at every possible wealth level, you must also reject any finite sequence of those exact same bets. The behavioral blind spot causing this paradox is called narrow bracketing. The colleague is evaluating a single bet in strict isolation, rather than analyzing the aggregated risk of the entire sequence. Narrow bracketing provides a mechanism for the equity premium puzzle. Historically, stocks have returned roughly 6% per year, far outperforming bonds. Under classical theory, the only way to rationalize holding bonds would be a risk aversion coefficient of 30,
a level far beyond what we observe in the lab. Benartzi and Thaler argue that if investors evaluate their portfolios annually, the frequent sight of short-term losses makes stocks feel riskier than they are, leading investors to demand a high premium to hold them. Behavioral economist Shlomo Benartzi and Richard Thaler proposed myopic loss aversion to explain this. Investors evaluate their portfolios too frequently. By checking annual or quarterly statements, the inevitable short-term losses feel disproportionately painful, blinding them to the long-term gains. It is an elegant hypothesis that makes perfect intuitive sense, but proving it requires a completely isolated laboratory experiment. To test myopic loss aversion, Ori Gnesi and Jan Potters designed the investment game. Subjects allocate an endowment to a risky bet. Two groups isolate feedback frequency. Treatment H makes decisions round by round, seeing results after every single bet. Treatment L locks in bets in blocks of 3, only seeing the aggregated combined outcome at the end. The underlying probabilities and the expected value of the bet are mathematically identical for both groups. The results showed that subjects in the low-frequency treatment invested nearly 17% more of their endowment into the risky asset than those in the high-frequency treatment. This confirms myopic loss aversion. Forcing people to aggregate their outcomes dampens the psychological weight of individual losses, directly increasing their willingness to take risks. The results of these 3 experimental models suggest that risk preference is highly sensitive to the conditions of the choice. Holt and Laurie demonstrated that risk aversion amplifies dynamically as absolute monetary stakes scale up. Eckel and Grossman proved that the cognitive complexity of how a gamble is framed can distort the accuracy of our measurements. And Gnesi and Potters showed that high-frequency feedback induces myopia, proving that when we evaluate a risk dictates how much risk we will accept. Policymakers and firms use these insights when designing pension plans, health insurance, and corporate compensation to align with human behavior. Risk preference is not a singular platonic trait waiting to be uncovered. It is actively shaped by the architecture of the choice itself. Expected utility models are only valid if we account for the context, the scale, and the frequency of the risk.